Hello, in this video I'm going to be working some parametric equation free response problems for AP Calculus. So, this looks like a robust set. 3 sheets of paper, so this could be a lot. Might have to do this one in 2 sittings, but that'd be alright too. Okay, this is, in general, it's going to require a bunch of calculator use, so get one of those ready. Okay, particle moves along a curve in the xy plane with position x of t and y of t at time t greater than or equal to 0, with dx dt is that and dy dt is this. Okay, I think we're going to be plugging dx dt and dy dt into y1 and y2. I think that's going to be the thing to do. So I'm going to plug that in there. Square root of 3t and 3 cosine of t squared divided by 2, and okay, yeah, that'll work. So the velocity at time 4 is going to be just x prime of 4, which is, I mean, everyone will accept if you call dx dt with 4 plugged in, x prime of 4, we know what that means, and y prime of 4. Okay. And, okay, x prime of 4 is easy enough. I don't need to use the calculator for that. I don't need to waste my time punching buttons, right? I can just say, okay, I plug in 4 into that, and that would be, well, the square root of 12. Actually, I probably don't need to use a calculator for this one either, because I can just say, all right, I know how to square 4, and I'm just going to say that that's 16 divided by 2 is 8, and so that's 3 cosine of 8. Whatever that is. Now, if we were going to need to use this later for something, I don't know, nothing in AP Calculus, we wouldn't use this later. But if we did need to use this and get a decimal number, then that's something we can use a calculator for, right? But acceleration at 4, we're going to want to take a derivative, and we don't want to take the derivatives of these things. Even though we could, we don't want to. So we're going to say this is x double prime of 4 and y double prime of 4. Which is going to be something I have to find using Math 8 on the calculator. So I'm going to go over here. Oh, no. That was a mistake. 3 cosine t squared divided by 2. And we're in radian mode. Always got to check when you hit those trig buttons. Okay, so I want Math 8 on y1 at the point where t equals 4. That's going to be 0.433. And then the y coordinate is, I'm going to press second enter so that it, just brings up the same thing. And then I'm just going to change this to y2. And then that would be negative 11.872. Okay, we can do that. So, next, okay, that's the end of that part. Find the position of the particle at time t equals 0. Okay, this is what we're probably pretty good at by this point, if we did all the examples in the notes packet. Okay, so x of 0 equals x of 4 plus the integral from 4 back to 0 of x prime of t dt. That would be the square root of 3t dt. But you could write x prime if you wanted. And then that would be, all right, so x of 4 was 1 plus the integral from 4 back to 0 of x prime I had in y1 dt, and that is negative 8.238. Okay, and y of 0 is going to equal y of 4 plus the integral from 4 back to 0 of y prime, which is up here. You can't see it, but it's 3 cosine t squared over 2. Okay. And so, well, what was y of 4? Y of 4 was 5. So I'm going to pretty much, I'm going to just call back for this and switch that to a 5 and switch that to y2. 1.601. Okay, the next one, between 0 to 4, at what time does the speed of the particle first reach 3.5? So I'm going to say speed is x prime of t squared plus y prime of t squared. And I don't want to, copy all that down, although it would be pretty easy to square x prime. y prime, you don't want to forget to square that 3 also, and we could just say that equals 3.5 since both of these things are already defined, and I'm going to use the calculator to help me out. So I'm going to go over here to y equals, and in y3, I'm going to say the speed. So that's the square root of y1 squared plus y2 squared. And I'm interested in where that equals 3.5, so I'm going to subtract 3.5 and find where it's equal to 0. Okay, I need to set my window for t to be running from 0 to 4. Right now, x is representing t on the calculator, so I'm going to do that. Oh, goodness. Okay, if this is happening to you and you're like, man, I do not want to sit and watch this thing graph the blue and red equations, a thing that you can do is... Is it ever going to happen? Okay, I thought it was going to happen there. A thing you can do is you can turn it off from graphing the red and the blue ones. Okay, so it happened, but man, it is graphing slowly. Okay, so I want to calculate the 0, but see, it's going to default to the blue curve. It's going to default to y1. So I got to scroll down. Okay, then it's the red. Now it's the black. Okay, that's a left bound. I'm going to scroll over to the right until it goes above the x-axis. That's a right bound. And the first time is at t equals 2.223. Okay. And then the total distance traveled is going to be, we're just going to integrate speed. So from 0 to 4, we're going to say integral from 0 to 4 of the square root of x prime of t squared plus y prime of t squared dt. And, well, I've got that mostly inserted into y3. Hey, I was going to show you how to, if you wanted to not graph y1 and y2, you go over and you highlight the equals and you hit enter, and then it's not highlighted anymore, which means it's not going to graph it. Okay, so I came in here to get rid of the 3.5 so I could just, integrate on y3. So I'm going to be integrating from 0 to 4 on y3 with respect to t. We can do that. It's taking a second to think. 13.182. Okay. All right, no calculator. A particle moves in the xy plane, so the position of the particle is given by this and that. Wow, that's a lot of exponentials. Find the velocity vector in terms of t and find the speed of the particle at time t equals 0. We can do that. Okay, velocity vector is x prime and y prime. So it will be 6e to the 3t minus 7e to the negative 7t. And I don't know why I was having trouble taking the derivative of that. That's 9e to the 3t plus 2e to the negative 2t. Okay, and the speed at time 0 is going to be equal to the square root of 6 times e to the 0 minus 7e to the 0 squared plus 9e to the 0 plus 2e to the 0 squared. Okay, that's negative 1 squared, that's 1. That's 11 squared, it's 121, so this is the square root of 122. Okay. Find dy dx in terms of t and find the limit as t approaches infinity of dy dx. Oh, that's slick. I like this problem. I don't remember working that one in the past, but I know I have. I don't have the key pulled up to the side this time. So I won't know if I'm making a mistake. So I'm going to write dy dx is going to be y prime divided by x prime. And I've got y prime and x prime listed here in my velocity. So dy dx equals 9e to the 3t plus 2e to the negative 2t over 6e to the 3t minus 7e to the negative 7t. All right, that's my expression for dy dx. And then the limit as t approaches infinity of dy dx. You're looking for the biggest thing on top and bottom. The biggest thing I'm seeing is 9e to the 3t and 6e to the 3t. So those essentially are the same, so I'm going to divide their coefficients. It's going to be 9 over 6. But as that's happening, you might be like, wait, what about these other exponentials? Aren't they, growing exponentially? And they are if t goes to negative infinity. But as t approaches infinity, this is like 1 over e to the 2t, right? And that is the type of fraction that would go to 0 as t went towards infinity. So I'm going to say this thing goes to 0 and that thing goes to 0 as t goes to infinity. And it probably wasn't good that I did that on my expression for dy dx, right? Because now I don't have an expression for dy dx anymore. But you know what I meant. So limit of dy dx is going to be 9 over 6. Had this been the limit as t approached negative infinity of dy dx, it would have been, those would have gone to 0. Oh, yeah, it would have been 0, but yeah, wouldn't need to talk about that. Okay. Find each value t at which the line tangent to the path of the particle is horizontal, or explain why no such value exists. All right, so horizontal is when dy dx equals 0. Maybe I'll say dy dx, which equals y prime of t divided by x prime of t is equal to 0. And that has to be when y prime equals 0. Okay. That's telling me I've got y prime all the way up here. This thing needs to be equaling 0. So I'm going to just say, all right, 9e to the 3t plus 2e to the negative 2t needs to equal 0. Okay. Yeah, that's not going to happen. That's just not possible. Let me make sure I didn't make a derivative error. 9 plus 2. Yeah, no. Because e to the 3t and e to the negative 2t are both positive numbers. Okay, so y prime equals 0 never because 9e to the 3t plus 2e to the negative 2t is greater than 0 for all t. And I don't think you would need to say for all t. I think it's implied if you just say it's greater than 0. Okay. Find each value t at which the line tangent to the path of the particle is vertical, or explain why none exists. Okay, so that's going to be where x prime equals 0. X prime, we said, was this thing up here, 6e to the 3t minus 7e to the negative 7t. I think this actually could work. So 6e to the 3t minus 7e to the negative 7t, but I might actually call that 7 over e to the 7t, is equal to 0. You can see, I think you can kind of see algebraically where this is headed. So this is 6e to the 3t equals 7 over e to the 7t. So I multiply both sides by e to the 7t and probably divide both sides by 6. So yeah, e to the 3t over e to the 7t equals 7/6. Okay, what's going to happen here is I'm going to use a property of exponents. If I have dividing two things with the same base and different exponents, I subtract the exponents. So I'm going to say this is now e to the negative 4t equals 7/6. I'm going to take the log of both sides and I'll get negative 4t equals the natural log of 7/6. And t is negative 1/4 of the natural log of 7 divided by 6. Okay. And that's how we would find that with no calculator. The second page, which is not taking as long as I thought it might take. So I might try to do this all in one go, or I might do 2 pages and save the third page for tomorrow, because there's only so many hours in a day. Object moving along a curve in the xy plane is at xy at time t with, oh my, that's quite a function there. Arc sine of 1 minus 2e to the negative t. Okay. All right, we can do that. Definitely going to be wanting to plug dy dt into y1 and dy dt into y2. All right, so arc sine 1 minus 2e to the negative t. All right, and dy dt is 4t over 1 plus t to the 3. And then I've got y3 being the speed, because that, I don't know, that'll probably help. I feel like it's a little dark. Yeah, I can probably brighten that up for y'all. And, all right, acceleration vector. I'm going to have to take the derivative of dx dt and dy dt to get the second derivatives. We've done this before. But I need to indicate, I'm going to use the calculator to do this, and I have to tell the reader that, what am I doing here? What calculus am I doing to get to my answer? It's x double prime of 2 and y double prime of 2, which means that, that's implying that you're going to be taking the derivative of dx dt and dy dt. And we're going to use math 8 to make that happen. So we're going to, I think we already did this once, math 8 on y1 at t equals 2, 396. And same thing, just with y2, negative 0.741. Okay, too zoomed in here. That'll work. Refocus it. All right, and the speed at t equals 2 is going to be equal to the square root of x prime of 2 squared plus y prime of 2 squared, which, oftentimes, I've got it in y3. I might as well just do it, right? I think, I could plug in 2 and write all those things squared, but I actually think it'd be just faster to say y3 of 2 equals that 1.208. Making sure that y3 is exactly what we want it to be. The curve has a vertical tangent at one point. When is the object at that point? Okay, well, that's where dx dt equals 0. And so I need to graph y1 and figure out where that's going. Okay, it's going to be t greater than 0. Oh, okay, well, yeah, I guess that is going to have a nice domain. Anyway, we want dx dt equals 0. So I'm going to not graph dy dt, not graph the speed, and just, who knows, maybe 0 to 4 will be enough. Let's see if it happens. Yeah, there we go. Okay. If this was just going really, really too slow for you, you could stop it by, trying to turn the calculator off. That's what essentially stops it, and then narrowing the window. But I'm patient. I've got plenty of time. 0 is to the left of it. 2 is to the right of it. The intercept is at 0.693. Okay. Let m of t denote the slope of the line tangent to the curve. Write an expression for m of t in terms of t and use it to evaluate. Very similar to the problem we just worked. So m of t is dy dx. Oh, I get why I didn't say that. So it's dy dt over dx dt. So, yeah, you can copy it if you want, or you can 1 minus 2e to the negative t divided by 4t over 1 plus t to the third. Okay, yeah, and you could call that dy dt over dx dt if you wanted. Now, I am feeling like this is, all right, as t approaches infinity, I feel like this is not going to exist because, okay, so I'll say, what's happening as t approaches infinity? E to the negative t goes towards 0 because that's like 1 over e to the t. So I'm basically taking the arc sine of 1. Now, if you had forgotten, how do I take the arc sine of 1? You draw yourself a little unit circle, like, where is sine equal to 1? Sine's equal to 1 up here. So that means it's pi over 2. Okay? So it's pi over 2 in the numerator, but in the denominator, this fraction is bigger on bottom, right? T to the third grows faster than 4t. As a result, I'm going towards 0, and I'm just going to real quickly check my work from last year and make sure I said that this limit failed to exist. But let me scroll too far. There we go. This one's number 11. I am such a fool. I was doing run over rise. Okay. Whoops. It's all right. Sometimes that happens. In that case, you probably want to scratch that. You definitely need to scratch out wrong work on like the quiz or the test or the AP exam or whatever. I'm just going to cover it. It's going to be all right. Okay, yeah, dy dt was the fraction and dx dt was the arc sign. That's too bad. So 4t divided by 1 plus t to the third. Okay, divided by, what am I doing here? Oh, arc sign. And that would probably be one good reason to at least start off with m of t equals dy dt over dx dt, right? In case you just copied them down wrong like I did. Okay, so I'm over here. I'm going to say that the limit as t approaches infinity of m of t is going to equal, okay, on top, this one's bigger, on like the fraction up here, this grows faster, so this one's going to 0. And the bottom is going to pi over 2 for reasons I was just talking about earlier, and so I'm going to say that this is 0. But you could stop there. Now, the graph of the curve has a horizontal asymptote y equals c, right? But don't evaluate an expression involving an improper integral that represents this value c. Oh, that's a good one. I like that. This is a good problem set. So what we're going to do is we're going to say, I don't know why I suddenly felt inspired to switch up the color, but let's switch to blue. And I'm going to say, all right, the horizontal asymptote y equals c, that is, oh, and this one said t is greater than or equal to 0. So I actually do know with certainty that, I don't know, maybe this is c. I'm hoping c is positive, but even if it's not, same idea. Okay, we're going to be approaching that over time, which means that the limit as t approaches infinity of y of t is equal to c, right? We know that x is going to approach infinity, but y needs to be approaching c. Okay? So I'm going to say, how do I get y? Especially since I don't have really an expression for y. Okay, I'm going to get y with the initial condition and the dy dt. So y of t is -3 plus the integral from 2 up to t of dy dt, except for the dummy variable. So I'm going to say that this is the integral to infinity, right, of dy dt, which was 4t over 1 plus t to the third dt. But there was an initial condition at time 2, the y coordinate was -3. And that's going to be equal to c. Okay? And, well, we know, I'm not sure if we're actually able to anti-differentiate this thing, but we are able to know that because it's bigger on bottom by 2 powers that this integral is going to converge. So it probably shouldn't be surprising. Okay, that was a good problem. I liked that one. Let's move on to the back side, calculator. Object moves along a curve in the xy plane, so its position is xy. Can't even see what I'm talking about here. With x prime is arctangent and y prime is log of something. Okay. Time t equals 0, the object is position -3, -4. All right, so I'm going to start by plugging these things into y1 and y2. X prime is going to be, let's see, is inverse tangent of t over 1 plus t. And y prime is log of t squared plus 1. Yeah. And, okay, I'm sure I'll need, speed, needing it right off the bat, so I'm not going to be clearing it out. Okay, still square root of y1 squared plus y2 squared. All right, find the speed of the object at time t equals 4. That's just evaluating y3 with 4 plugged in, and yeah, there you go. Okay, but, we can't just write 2.912. That's not ever going to be acceptable in my class, in this class, in any class, right? We're going to need to show the work that leads to our answer. So we're going to say the square root, speed is that square root of x prime of 4 squared plus y prime of 4 squared. That's all you got to show. I have to write a dissertation on it. We just got to show a little bit of evidence. So it's 2.912. Okay. Find the total distance traveled by the object over the time interval 0 to 4. Well, we're just going to integrate speed, which is in y3 already, but we're not going to just write y3 because we know the reader. They don't speak calculator. So it's going to be x prime of t squared plus y prime of t squared. Okay. Bring this over here. Integrate from 0 to 4 on y3 respect to x, and it's going to be thinking, and it's 6.423. All right. Find the position of the particle at t equals 4. Right. X of 4 equals, they gave us the position at time 0, so I'm going to start with x of 0. Plus the integral from 0 to 4 of x prime of t dt. That was the, you know what, I think I'm just going to write it like that. I don't want to copy arctangent of t over 1 plus t. That's just too much, right? So x of 0 is -3. 0 to 4. dx dt is in y1. -0.892. And y of 4 equals y of 0 plus the integral from 0 to 4 of y prime of t dt, and that's, okay, what was y? It's -4. Okay, yeah, so just kind of run this thing back, and okay, I'm changing y1 to y2. I'm changing -3 to -4, and otherwise it's the same integral, 1.984. For t greater than 0, there is a point on the curve where the line tangent to the curve has slope 2. Okay, so dy dx equals 2. At what time t is the object at this point? Find the acceleration vector at this point. Okay, well, I'm sure we can do that. So let's say dy dx equals 2. So that tells me that y prime over x prime is equal to 2. That gives me t equals, well, I don't know, I'm going to have to solve that equation. But I'm going to go in and clear out y3 and have that be a fraction of y2 divided by y1. And I want to know where it's equal to 2, so I'm going to subtract 2 and find where it equals 0. I'm also going to turn off the graphing on this, so I don't have to watch it graph those things. I don't know what they look like, but I'm sure they're pretty wild functions. So we're going to, let's see, we said t greater than 0. I bet it'll happen sometime between 0 and 4. It just happened to be what my calculator window was last set at. And we're waiting patiently. Calculating a 0 between 1 and 2. And that is 1.358. Okay, I'm copying all of the decimals because I want to use that number, so there's I know there's no round off error. Okay, and also if we found this 0 in here, I mentioned this in the maybe 2 units ago or something. We were doing a bunch of area volume, but I recently learned that when you do that 0, I don't know about the 0 actually. I may be lying to you. Let's test it out. But when you do the intersection, it stores those numbers into x and y. So let's see if when I press x, it gives me 1.3576631. Sure enough, and it gave me 2 more decimals of precision. So I'm going to go over here and say, all right, well now I want, okay, acceleration vector is going to be x double prime of 1.3576 ... and y double prime of 1.357, whoops, 6 ... It's supposed to be a 7. It's looking worse and worse. Okay, yeah. Let's be happy with that. And so we're just going to do math 8. And that's I don't know about the kind of redundancy with x equals x. So I'm going to take that number and I'm going to store it into letter A, because that makes me feel safer. And so I'm going to math 8 with respect to x. That's what I'm concerned about, is the the kind of circularness of that. But it's all right. I get 0.135. And the y coordinate would be basically the exact same thing, but I'm going to change that to y2 and 0.955. Okay, and that's the acceleration vector at the magic time they were talking about. Okay, well, you know what? I'm only half an hour in. I've recorded much longer homeworks, so I think I'm just going to try to go for it. Knock it all out in one go. Although I don't recommend that for you, right? This is 6 really good free response questions, and I would recommend doing a few of them today and a few of them before the test, right? And don't try to eat the whole buffet in one sitting. So an object moves along a curve with position x, y. Did I not? Okay, all start off the same. And that's what I've been telling y'all, is that these problems are very repetitive and therefore predictable, and that's why I like them. Okay, oh, y prime not explicitly given. Okay, I like these problems. Okay, so x prime, I'm going to just clear that out. I don't be needing that. Okay, so x prime is 2 plus cosine of t squared. Okay. Find the x coordinate of the position of the object at time t equals 4. X of 4 equals x of 2 plus the integral from 2 to 4 of x prime of t dt. Okay. So, I mean, I don't think you need to write this, but I'm just to be explicit, 1 plus the integral from 2 to 4 of 2 plus cosine t squared. And that's going to be, all right, 1 plus math 9 from 2 up to 4 of y1 dt. All right, 5.133. At time t equals 2, the value of dy dx equals -7. Write an equation for the line tangent to the curve at the point x of 2 and y of 2. Oh, okay, I misread that. I read that as dy dx, which would have been interesting. But then if they wouldn't have asked you for the line tangent, they would have asked you, if they gave you dy dx, they would have asked you for dy dt, and you'd have to solve backwards for that. And that would also be a good problem. I don't know. I've seen a problem like that out there somewhere. Okay, so at time t equals 2, well, slope is dy dx at time t equals 2. It's going to be dy dt is -7 over dx dt is, well, just x prime of 2 is what I'll just say, because I'm going to use the calculator for that. Okay, in y1 I've got x prime of t, so I just need a fraction bar. On top I've got -7, and in the bottom I've got x prime of 2. I'm going to get -5.199. Okay. And yeah, now I'm realizing that I could also have said that x prime of 2 is 2 plus cosine of 4. And maybe I'll do that. Okay, for the most, exact, yeah, we've got the point is 1 and 8. The slope is that, so the equation is going to be y minus 8 equals, you could put this, or you could put -7 over 2 plus cosine of 4, right, just plugging in 2 for t there, times, and this is just a number, right, it's the same as -5.199, x minus 1. I mean, that's how I'd write the tangent line. Find the speed of the object at time t equals 2. Well, that's going to be the square root of x prime of 2 squared plus -7 squared. Okay, so 49 plus, well, I didn't put in the square root, but that's all right, because I can plug in 2 for that, and then take the square root, and I'll get 7.096. this last one is at time t greater than or equal to 3, the line tangent to the curve at x and y has a slope of 2t plus 1. Okay, so line tangent has a slope, that means dy dx is equal to 2t plus 1. At time t equals 4, dy dx equals 9. Okay. Acceleration vector of the object at time t equals 4. I'm not seeing what to do here. Huh. What does the 9 have anything to do with this? Okay, yeah, that's a little weird. All right, oh, 2t plus 1. Oh, yeah, okay. Man, this one's a little tricky. Okay, so, but we know also another expression for dy dx. dy dx is equal to y prime of t divided by x prime of t, which x prime of t is 2 plus cosine of t squared. Yeah, we're going to set these two things equal to each other. See what happens. So y prime of t over 2 plus cosine t squared is going to equal to t plus 1. And then I can solve for y prime of t by multiplying over there. So now I've got y prime of t equals 2 plus cosine of t squared multiplied by 2t plus 1. Okay, now in order to find the acceleration vector, I need the second derivative, and I thought we'd already done that, but I guess that was a different problem. I'm going to find the x-coordinate just using, you know, the x-coordinate of the acceleration by taking the derivative of x prime, right? Because we know that the x-coordinate of acceleration is x double prime. So x double prime of 4 is going to be the derivative of y1 at t equals 4. And I get 2.303. Oh, okay. And I do need to describe how I got this, right? I have nowhere said, hey, I'm going to take the derivative of x prime to get that. So I'm just going to go over here, and I'm going to need a thinner pen. I'm kind of running out of room. So I'm going to say, I can even just say a of t in general is x double prime of t and y double prime of t. And I'm going to use that to justify this. Like, hey, I'm going to take the derivative of x prime and plug in 4 to get 2.303. That's all it takes. So then, though, I need to take y double prime, which is going to be taking the derivative of this. Now, a thing that we could do to make our job a little bit easier would be just kind of call for the same thing, except over here, I'm going to tack on a 2t plus 1. So times 2t plus 1, and I get 22.671. Which is what I got last year, so that's a good sign. All right, and all right, one more page. Oh, it's 2 more figure response problems. Okay, we can work with that. We're not scared of some work. So curve gamma is given by gamma of t is t plus 2 over t and 3t squared for t greater than 0. Okay, find the coordinates of each point on the path where the velocity of the particle x direction is 0. Okay, that just means dx dt equals 0, or the derivative of this equals 0. So no calculator. So I guess I'll just say, nobody said anything about a particle moving, but I think this is just part of a question that I clipped. So Vx is the derivative with respect to time of t plus 2t to the negative 1, which is going to be 1 minus 2t to the negative 2. Okay. Okay. We're just going to be interested in this thing equaling 0. So I'm going to add the 2t to the negative 2 over there, but I'm probably going to rewrite it as a fraction. So this tells me that 1 equals 2 over t squared. So that means that t squared needs to equal 2. T is a positive number, so t is the positive square root of 2. And then we're going to find the second derivative of y with respect to x when y equals 12. Okay, now, again, y equals 12 is not a value of t. So I got to go over here and say, all right, 3t squared equals 12. That's t squared equals 4, so t could be 2 or negative 2, but I know that t has to be positive, so that's just going to be t equals 2. Okay, now I need to say, all right, well, dy dx, I can just already tell I'm going to need more room, so I'm just going to switch to a thinner pen. So y prime equals 6t. I'm going to take that derivative. X prime, we already took that derivative. That was 1 minus 2t to the negative 2. Oh man, no calculator, huh? All right, well, you know what? I'm going to rewrite this. 1 minus 2 over t squared, because I think I might end up trying to maybe not like fully simplify the dy dx, but do some work on dy dx to make it easier to take the derivative of, because I know that to find the second derivative of y with respect to x, I'm going to have to take the derivative of dy dx and divide by dx dt. So maybe we can find something good there. All right, so dy dx is equal to 6t divided by 1 minus 2 over t squared. Yeah, I think I might just multiply this by, you know, some kind of form of 1. But if you want to just take the derivative of this using the quotient rule, you can be my guest, you know. And so this is equal to 6t to the third divided by t to the 2 minus 2. And this is something I might... You could synthetic divide that if you wanted, but at a certain point, you're just doing a bunch of... You have your pick. You're going to do hard work on calculus, or you're going to do hard work on algebra. Like, what's it going to be? There's no avoiding it. So we know that the second derivative of y with respect to x is going to equal the derivative of dy dx divided by dx dt. Okay. The derivative of dy dx, I'm going to use the quotient rule, bottom times the derivative of the top. The derivative of the top is 18t to the 2. Bottom times the derivative of the top, so t squared minus 2. Okay, minus the top times the derivative of the bottom would be 6t cubed times 2t. Divided by the bottom squared. T squared minus 2. And divided by dx dt. Okay, we know that we could put it over this, but it'd be like multiplying by 1 over it, so I'm just going to actually put that in the denominator. And if you're not okay with that algebra step, just come talk to me, and I'll show you why it was legitimate. Dx dt is 1 minus 2 over t squared. And at this point, I'm just going to be plugging in t equals 2, so that's a perfectly fine way to express that. Okay, so the second derivative of y to x at t equals 2, which is the same as y equals 12. That's going to be equal to 18 times 4 times 4 minus 2 is 2, minus 6 times t to the 3 times 2t divided by t squared minus 2 squared multiplied by 1 minus 2 over t squared. And that's going to be a suitable answer for us, especially in a non-calculator scenario, right? You could spend some time figuring out what that number is, but you might make an arithmetic error, or you might just be wasting your time. Okay, so at time t, this last one, this is kind of graph. Okay, yeah, I like the mixed media one, where they give you an equation and they give you a graph. I very likely will give you something like that on the unit test. All right, so dx dt is given. It's that negative 12 over t squared. And dy dt is this graph. And they gave us an initial condition. Find the position of the particle at time t equals 2. All right, we can do that. So x of 2, okay, yeah, I gave plenty of room throughout the whole assignment, but now it's not nearly enough room. So x of 2 will equal x of 1 plus the integral from 1 to 2 of x prime of t dt. So that's negative 12t to the negative 2. All right, and we're going to add 1 to the power and divide by the new power to get an antiderivative. Right. And so that's going to be 12t to the negative 1 as t runs from 1 to 2. Well, that's not so bad. So that'll be 5 plus, okay, 12 divided by 2 is 6, minus 12 divided by 1 is 12. Okay. That's the x-coordinate of the position. Y of 2 equals y of 1. Hold on. Yeah, y1 is 1. Plus the integral from 1 to 2, I don't know, maybe I'm missing something, but okay, right here, the integral of dy dt, or I'll call it y prime of t. Okay, well that's going to be 1 plus, that whole integral is the area under the curve between 1 and 2. It's going to be negative 1. And that position is 0. Okay, wasn't very interesting, but it's all right. Find the slope of the line tangent to the path of the particle at t equals 2. They want you to say it doesn't exist because of a sharp corner, but that's not what this is telling you. This is not the path of the object. This is dy dt versus t. So we're going to say that the slope of the tangent line, that is dy dx at t equals 2. Is y prime of 2 divided by x prime of 2. We've got y prime of 2, that's negative 1, right? This is the graph of y prime of t. So we might even label that, y prime of t versus t. Okay, y prime of 2 is negative 1. And then x prime of 2, what is x? Oh, x prime of 2 would be negative 12 over 4 is negative 3. And that's the slope. Okay, and then find the speed of the particle at time t equals 3. Well, the speed is going to equal the square root of x prime of 3 squared plus y prime of 3 squared. Okay, x prime of 3 is going to be negative 12 over 9. This is no calculator, and so I'm just going to write that, plus dy dt at t equals 3 was negative half squared, and that's a suitable expression, right? That's going to be good enough for us. And look at that. That is all of the problems I've got. Okay, that was a pretty robust homework set. I hope you found it to be illuminating. I really think that almost all of the scenarios that could come up in a parametric free response problem came up right there. But, you know, if you need more practice, you should probably the Unit 10 free response booklet, Unit 10 multiple choice booklet, email me and I can send you some more stuff. But, you know, maybe, just maybe, you can be satisfied with the work we did today. Thanks for watching.